So in office hours today, we're going to work through a couple of integration examples. I'm going to start with 7.1 number 5. This is an example similar to one that I posted in one of the videos, but I think it's worth going through the process with this particular example. So for this problem, we're going to use integration by parts. And as a reminder, what is the formula for integration by parts? It's the integral of u dv is equal to uv minus integral of v du. And if you recall from the video, this comes from product rule. We have a product here. Product rule for differentiation turns into integration by parts when trying to integrate a product here. So the goal with integration by parts is I'm going to look at my original integral and I'm going to piece apart which piece do I want to become my u and which piece do I want to become the dv. In this case, maybe I'll rewrite this integral down here. And in most cases, it actually turns out that it doesn't matter which order I pick it in, that we could use either. But I always set it up with u equal to something and dv equal to something. And these are the two pieces that I'm picking here. I'm going to pick, maybe this is opposite of what I did in the video, but I think it's helpful because it shows you the flexibility of this rule, that I'm going to let u in this case be equal to the piece e to the negative 6x, and I'm going to let dv be equal to the other piece, which is the sine of x. So I picked out u and I picked out dv. On this side I'm going to take the derivative, because the derivative of u gives me my du. What's the derivative of e to the negative 6x? The derivative, I'm going to have to apply chain rule. It is just e to the negative 6x. By chain rule, I multiply by the derivative of the exponent as well, negative 6. Over here, this is dv, so I'm going to work backwards and take the antiderivative. Derivative t. Okay. So the antiderivative of sine, recall that the derivative of sine is cosine, so the antiderivative is going to be negative cosine of x. So my original integral, I picked out my pieces. One of the pieces becomes u, one of the other pieces became dv. And looking back at this formula for integration by parts, I can now fill out the rest of the pieces. It means that my original integral is actually exactly equal to u times v. In this case, u is e to the negative 6x times v, negative cosine of x, minus the integral of v, which is again negative cosine x du, which is negative 6 e to the negative 6x dx. I'm going to simplify this one step. Keeping this here, this becomes negative cosine x e to the negative 6x. And then let's see, I have a negative times a negative is positive, so I'm just subtracting the integral of 6 cosine x e to the negative 6x dx. So like we saw before, I did one set of integration by parts, and I came up with this new equation that isn't all that helpful. It turns out I need to integration by parts a second time on this piece to complete the problem. So continuing, let's do integration by parts a second time. I'm going to set up my u and my dv, because in this integrand I need to pick out a u and a dv. For simplicity's sake, instead of leaving the 6 on the interior, we can always pull the 6 out front, and I think that makes it easier in this process around with me. If I did, it wouldn't be that big of a deal. Let's pick the same pieces that we did last time. Last time we let our e be the u piece, and we let our sine be the dv, so we'll let our cosine be the dv this time around. So u is equal to e to the negative 6x. du is the derivative of that, which is negative 6 e to the negative 6x. Again, that's chain rule. My dv piece, I guess I did it in red last time, is cosine x. So I'm going to take the antiderivative. What's the antiderivative of cosine? It's negative sine, right? The derivative of cosine is negative sine, so the antiderivative of cosine is just regular sine, sine of x. So now I have these pieces, and I can look back at my formula to tell me how do I do integration by parts. My pieces work out as uv minus the integral of v du. So completing this, I'm going to write out all of the work though. I want to keep it all in one line so that I don't lose track of any of the pieces. My very first original integral. This is what I got from the first by parts. I got e to the negative 6x times cosine x. That piece is all negative. And then I have minus 6 times this integral. And this integral I'm going to rewrite as u times v, which in this case is e to the negative 6x sine x minus the integral of v du. So v is sine of x, and du is negative 6 e to the negative 6x dx. And again, I'm going to simplify this a little bit. This 6 I need to distribute both to this term and to the integral term. So being careful with that simplification process, I end up with negative 6 e to the negative 6x sine x. I have this term from the first integration by parts, this term from the second integration by parts. I don't need to integrate. Here I have a negative, and a negative makes this positive, but then I'm subtracting by 6, so this becomes minus 6 times 6, which is minus 36, times of 6 times sine x e to the negative 6x dx. And let's double check to make sure that arithmetic is correct. So here in this integral, I can pull the 6 out front of the integral, and it becomes minus a negative is positive. So I should have 6 times this, but then I'm multiplying it by negative 6, so I get a negative 36. That looks correct. Why is this interesting? This is interesting because this value right here, this integral, is the one that we're trying to solve for. I could rewrite this sort of in colloquial language. I could think of this as one big variable. I could think of it as like a big variable a. And this statement is saying that a is equal to negative e to 6 cosine x minus 6 e to the negative 6 sine x minus 36a. If I were solving for a in this expression, what would I do? I would add, well, maybe this is what I would do. I would add 36 to both sides, 36a to both sides, and I would get 37a is equal to negative e to the negative 6 cosine x minus 6e to the negative 6 sine a. I'm going to divide both sides by 37, and I get a is equal to 1/37 e to the negative 6 cosine x minus 6 37ths e to the negative 6 sine x. And why did I use an a instead? I'm using an a really just because I think it's shorter than having to write out this big, long, messy integral every single time when I'm doing this computation. But you could leave the integral in place in each of these places. And it means that we get our final solution, which is that our a value, the integral of e to the negative 6x times sine of x dx, is equal to negative 1/37 e to the negative 6 cosine x minus 6/37 e to the negative 6 sine of x. And that's our final answer. So the other problem that I wanted to work through is one that is sort of a tedious trig integral. I say tedious because in this case, the 7th, it's an odd power. So in my head, I'm thinking to myself that I want that cosine squared of x is equal to 1 minus sine squared of x. And in this case, it's not x, it's 3x. So I'm going to use the fact that cosine squared of 3x is equal to 1 minus sine squared of 3x. And I'm doing this because I need to get a u substitution somehow, and I know that if I picked cosine to be u, then sines would be du's, or if I picked u to be sine, then du would be cosine. So this is a good start because of the relationship between sine and cosine. The problem is, as written, cosine to the 7th, I'm going to write it out in sort of a crazy way. I'm going to rewrite this as cosine squared of 3x times cosine squared of 3x times cosine squared of 3x times, let's see, that's 2, 4, 6 cosine of 3x dx. Because I don't have any identities that deal with cosine to the 7ths, I only have identities with cosine squareds. So I'm being really explicit about the fact that I'm breaking my cosine to the 7th up into 3 copies of cosine squared times another copy of cosine. And this is where I can make use of this trig identity. I haven't done any calculus yet, there's no integration. I'm just algebraically rewriting each of these pieces. And I guess I'll do it the long way. But you get the idea that each of these cosine squareds I'm turning into a sine squared. But I still have this single term of cosine, which is nice. I'm going to use that to be my du. So we have a nice setup here. We have a bunch of sine squareds sort of embedded in these messy functions. Wouldn't it be nice, instead of having these sine squareds, I'm going to let u be equal to the sine of x, because that means that du, the cosine of x, oh wait, you can't quite be sine of x. I actually want it to be sine of 3x, because each of these have 3 x's in there. That means the derivative is cosine of 3x, but by chain rule, it's also the cosine of 3x times 3 dx. And I have a cosine of 3x dx here, but I'm going to need to multiply this extra factor of 3 in order for my u substitution to work. So to do that, I'm going to cleverly multiply, and that means I also need to multiply by 1/3. Multiplying by 3 and 1/3 doesn't change the value of the integral. And I can rewrite this using the u substitution. So anywhere where I saw a sine of 3x, I can change into 1 minus u squared. And the 3 cosine 3x dx becomes the du. So you asked me, why didn't I just write this as 1 minus sine squared to the 3rd? And I absolutely could. I could have this as 1 minus u squared to the 3rd. The reason why I kept it written out is because of the fact if I were, maybe I'll write this as scratch work to the side. This is sort of my thought experiment. If if I were integrating 1 minus u squared to the third du, there isn't actually a fast way to integrate this, that you might want to do a second u substitution, a double u substitution, but I don't have a u hanging out anywhere to be able to, like if I let my w be equal to u squared, then my derivative with respect to w would be 2u du. This is like me thinking about doing another u substitution, and there's no 2u piece here, so this doesn't quite work. I can't do a second u substitution. Instead, I'm actually just going to use algebra, and I'm going to multiply out this polynomial, and I'll do it piece by piece. First, I'll multiply the first two factors, and I get 1 times 1 is 1, and then I get minus u squared, and minus another u squared is minus 2u squared, plus u to the fourth, and minus u squared. And we like polynomials, just use power rule. But I have to multiply out again. So notice, I still haven't really done the integration. I'm still just doing algebra. This becomes 1 minus a u to the fourth, minus, maybe I'll do it in order. Okay, 1 times 1 is 1, minus 2u squared minus another u squared becomes minus 3u squared. And then I have minus a negative is plus 2u to the fourth plus another u to the fourth becomes plus 3u to the fourth. And then finally, u to the fourth times negative 2, or u squared becomes negative u to the sixth du. So the hard long part isn't the integration. The hard long part actually in this case was multiplying out a polynomial. But now that we have that polynomial multiplied out, we can just do power rule for integration. So this becomes u minus, when I raise that up to the third, I end up actually just getting u to the third, because that exponent, or the coefficient cancels, plus this becomes u to the fifth, so it's 3/5 u to the fifth, and 7th u to the seventh. And this is an indefinite integral, so I don't have to worry about bounds, but I should add on plus c. Then in my final step, I'm going to substitute back in the fact that what was u, my original u, is actually the sine of 3x. So looking at this, this becomes 1/3 times the sine of 3x minus 1/3 times the sine cubed of 3x plus 1/3 times 3/5 becomes 1/5 times sine to the fifth of 3x minus 1/21 sine to the seventh of 3x plus c. And we're done. The reason why I want to pull up this example also is the fact that if we wanted to, we could have, maybe looking backwards, we could look at our original integral and say, you know, this is something that I don't feel like integrating. Maybe it's something that I could use a table to be able to integrate. I'm going to have to do a u substitution to use the table because here I have a 3x and I don't want a 3x. Finding this on the table, my table tells me that the integral of cosine to the n is equal to cosine to the n minus 1 x sine x over n plus n minus 1 over n times the integral of cosine to the n minus 2 x dx.